All right, so welcome back. So in the previous lesson, we had a look at how to find the indefinite integral, and we established the relationship between the indefinite integral as well as the general antiderivative and how they're related to each other. We also had a look at how to use some of the techniques of integration to actually find some integrals. So the first one we had a look at was the substitution rule. And then the second one that we had a look at was the integration by parts. And we use both the tabular and the DI method and the regular way to find the integral of a function. So in today's lesson, we're actually going to be continuing on with our techniques of integration, but we're going to be having a look at our trigonometric integrals in this first part. Okay, so sometimes different combinations of trigonometric functions require different substitutions. For example, let's say we take the integral of cos cube of x d of x. So although one might be a little bit stuck on this part, what you could actually do here, first of all, is take the integral of cos squared of x and then the cos of x dx. So see here, cos squared of x, I could actually write this as cos squared of x, which is 1 minus sine squared of x, right? So that's by the Pythagorean identity. So once I write that down, I have 1 minus sine squared of x multiplied by cos of x d of x. So now I could actually apply substitution here. So I'm going to let u be sine of x here. So I'm going to say let u equal to sine of x here. Then that means du is going to be cos x d of x. And so we have everything that we need. So this du is going to be cos x dx here. This u is going to be this sine of x here. So that means if we put that all in, we just get the integral of 1 minus u squared du. And then this integral just becomes one of the easier integrals that we could actually evaluate. So this is just going to be u minus a third u cubed plus c. And then once we undo the substitution, we have sine of x minus a third sine cube of x plus c. And that's for this first integral here. But let's have a look at the second one. It looks a bit more challenging here. Well, whenever we have sine here, so we have sine to the fifth power now, and then we also have a cos squared of x. So first of all, let's write the sine to the fifth of x as follows. So I'm going to write this as sine to the 4 of x multiplied by sine of x, and then cos squared of x d of x. Now, remember that, well, sine squared of x, so let me put this here. So we know that sine squared of x is also 1 minus cos squared of x. So if we square it again, so square this entire thing, this side is going to be sine to the 4th of x, right? So that means we're going to get this part over here. So let's go ahead and put that. So we have that the integral of 1 minus cos squared of x squared of a sine of x and a cos squared of x and dx. So now we could apply a substitution here. So I'm going to say let u equal cos of x. Then that means du is going to be negative sine x dx, or negative du is sine x dx. So applying the substitution, we would get 1 minus u squared multiplied by another u squared, and we would have a minus du here. Okay, and so once we expand all this, we would get, so we get negative of the integral of 1 minus 2u squared plus u to the fourth, u4, du, negative integral of u squared minus 2u4 plus u6 du. And then once you evaluate this, so I'm actually gonna try to make some more room here if I can. Yep, there we go. And so if I just evaluate this integral, I would get a third and then I'm also going to undo the substitution here as well, just to make it a little bit cleaner. So we have a third. So since we let u be cos of x, so it's going to be cos cube of x minus 2 multiply, so 2 over 5 cos to the fifth of x, and plus 1 over 7 of cos to the 7th of x. And I'm also going to actually apply the negative sign as well. So this is going to be a negative, and then the second term is going to be positive. Second term's, the last term is negative. And don't forget the plus c as well. All right. So now let's have a look at the third one. So we have the integral of cos squared of x, right? So let's try to go back and think about the double angle formula for cos squared, cos of 2 of x. So recall, I'm going to do it down here. So recall this formula. We have cos squared of x, or cos of 2 times x. This is also the same as cos squared of x minus sine squared of x. But also, this is also the same as, so that means, so we also have 2, so we also have 2 cos squared of x minus 1. So that means if you were to solve for cos squared of x here, so that means cos squared of x is also the same as cos of 2x plus 1 divided by 2, right? So let's go ahead and plug that in. So we have the integral now of 1 plus cos times 2, cos of 2 of x, 2x divided by 2 dx. And so if we break up the integral into 2, the first integral, we would just get half of x. As for the second integral, we would get half, and then we take the integral of cos of 2x, which is then going to be half, so a half x. So we have 1 over 2 sine 4x, or of 2 of x, which is just going to be, well, half of x plus a quarter sine of 2x plus c. So whenever we're dealing with an integral that involves a cos squared of x, it is much easier to actually transform into 1 plus cos 2x divided by 2 using the double angle identity here. So it's also worthy noting that we also recall the half angle formulas as well. So the half angle formulas are as follows. So we know that cos squared of x is equal to 1 plus cos 2x, all this divided by 2. As well, we also have sine squared of x, which is equal to 1 minus cos 2x divided by 2. So that's the two angle identities we would need to know. As well, this one would also be helpful. We also know that sine x times cos of x is simply just going to be half of sine 2x. So those are some formulas that we would have to keep in mind. So this is 1, this is 2, and then this is the third one. All right. So we can form some rules for integrals of the form sine m of x times cos n of x dx. So for the first one, let's say that if m is odd, then we would have to change sine squared of x to 1 minus cos squared of x, and then solve, and we also have to say 1 sine x. So that way, as a result, so the result here is that, well, if we have the integral, once we change these sine m of x, so we would have 1 minus sine squared of x, or 1 minus cos squared of x, sorry. And this is raised to the power of k. And then we also have a cos n of x. And then we save 1 sine of x here, dx. And then once we have this, we could actually go ahead and substitute for u is equal to cos of x, and then du is negative sine of x d of x. So then we substitute. U is equal to cos of x, and then du is negative sine of x dx. So that is for the first rule. The second rule is, now instead of having m being odd, let's see what happens if n is odd then. Then we would have to change the sine of x, or change the cos squared of x to 1 minus sine squared of x, and we would have to save 1 cosine this time. And so as a result, we would have the integral of sine of m of x, or sine to the power of m of x, and then we would have 1 minus sine squared of x to the power of k. So k is just going to be the result after taking changing the cos squared into 1 minus sine squared. And then we also save 1 cosine of x. So we have a cos x dx on the outside. Okay, so now the thing that we substitute now is we're going to substitute for sine this time. So we're going to substitute u is equal to sine of x. So that means du it's just going to be cos of x dx. So that's the third rule. Now, for the third rule, let's say that both m and n are even. So if m and n are even, so both of them are even, use half angle identities. Or if both of them, m is equal to n is equal to 1, then we use the double angle for sine. Right? So we have seen this in the case from the previous examples that we had a look at. So here, the first example where we would have n being an odd and m being 0 here. The second example is where m is an odd and n is an even number, but doesn't really matter. And the third one is when n is even. So then we would have to use the half angle identities. All right. So those are the three rules for this integral here. So this is the integral where we had a look at. All right. So now let's have a look at what we could do with the tan and the secant now, because they have similar relationships with each other. So for the tan, let's say we have tan to the fourth of x and secant to the fourth of x. So let's recall that secant squared of x is also the same as 1 plus tan squared of x. Right? So let's go ahead and do a substitution or put that in. So I'm going to break up the secant to the fourth of x. So we have the integral of tan to the fourth of x. We have a secant squared of x. And we also have a secant squared of x here. And d of x. So I'm going to make the substitution here. So we have the integral of tan to the fourth of x. We have 1 plus tan squared of x. And then we also have a secant squared of x dx. And then we're going to make a substitution here that if we so we're going to let u equal to tan of x. So that means du is going to be secant squared of x multiplied by dx. So we see here now, we're going to let secant squared of x dx, which is this part here, that's going to be our du. And then everything else here is going to be our u now. So as a result, we're going to obtain, so we have u to the power 4. We have 1 plus u squared du. And so if we expand this, we get u to the power 4 plus u to the power 6 du. And so if we evaluate this, we get, and undoing the substitution as well, we get 1 over 5 tan fifth of x plus 1 over 7 tan to the 7th of x, and then plus c at the end. So that is the integral that we should get. Okay, so let's have a look at the second example here. So say we have the integral of tan cube of x times secant cube of x. Now, let's see. So say we break up the tan cube of x now. So we have the integral of tan squared of x multiplied by tan of x, and then multiply that by secant cube of x dx. Well, also noting that from this angle identity up here, so talking about this one, that we could say that, well, tan squared of x then is just going to be secant squared of x minus 1. So I'm going to write that down in place of the tan squared of x. So we have secant squared of x minus 1. We have a tan of x. And we have a secant cube of x here. And then dx. So it should be pretty clear what we're going to substitute here. We're actually going to be substituting our secant here now. So we're going to say let u equal to secant of x. Then that means du is going to be secant of x, tan of x, dx. So also observe that for the second part here, I'm also going to say, well, secant squared of x minus 1. The tan of x we're going to save here. And I'm also going to say, well, I'm also going to have a secant out here, secant of x. And then I'm going to have a secant squared of x as well. So that way, the secant of x, tan of x here can just be substituted by du. So we still have the secant squared on the outside, which will just be the u. And we would just have this much and this much to work with. So what that becomes now is just going to be the integral of u squared minus 1. Multiply that by u squared du. So that is the integral of u4 minus u squared du. So evaluating and undoing the substitution, we would get 1/5 secant to the 5th of x minus 1/3 secant cube of x plus c. And that is the integral we'll have here. All right, so similar to the one where we had the sine and the cosine, we could also make rules for tan and secant of x as well. All right, so let's consider the case when n is even. If n is even, then we're going to change the secant squared of x to 1 plus tan squared of x. And save 1 secant squared of x. And as a result of doing this, we would get that the integral of tan to the power m of x, and we have a secant squared of x, all that to the power k, and we're going to save a secant squared of x dx. Okay, so now it should be clear here that we're going to actually be substituting tan here. So we're going to substitute u for tan of x. And so that means du is going to be secant squared of x dx. All right. And as for the second case, we're going to assume that m is odd. So if m is odd, we're going to change the tan squared of x here all the way to, so we're going to have a secant squared of x minus 1. And we're going to save a secant x tan x. So as a result, the integral will then become, so we have the integral of a tan squared of x to the power of k we have a secant n of x, and we have a secant x tan of x. So now we're going to substitute here. So we're going to say let u be secant of x. So that means du is going to be secant x tan of x dx. So those are the two rules that we had looked at earlier. So we see that when n is even, so that follows from this example. So we broke it up. And then so we would have 1 secant squared of x here and the dx. So we save that. And we would just evaluate, do the substitution as well. For the second one, we see that, well, the 3 here is going to be the odd one. So 10 is odd. So that means we take a tan squared, take a tan, so that we could have a secant x tan of x dx here. And then we would just go ahead and make the substitution and then evaluate. All right, so that's for the next part here that we had a look at. Okay, so finally, let's have a look at the third scenario where we have to evaluate the integral of sine 4 of x, sine of 4x multiplied by cos of 5x, and then dx on the outside. So this comes from one of the angle formulas for trigonometric functions here. So let's have a look at this one. If a here, we're going to say if a is equal to 4x and b is equal to 5x, then we could actually go ahead and evaluate this. So this is actually going to be half of the integral. And I'm going to have here, for the first one, sine 4x minus 5x. And as for the second one, I'm going to have a sine x, or sine 4x plus 5x, all that dx. And so that means we have half of the integral of sine of negative x plus sine 9 of x, 9 times x dx. So that means, so since n is an odd function, sine is an odd function, we could bring out the negative sign. So we had the integral negative sine x plus sine 9x dx. So evaluating this, we could just go ahead and evaluate each of them. So we would get half of cos of x minus 1 over 9 cos 9 of x, 9x, and then plus c. So whenever we're evaluating integrals of the form sine mx times cos nx dx, there are 3 identities that we would use in this case. So we use the identities. So for the first one, we would actually be using this formula. So if we have sine A multiplied by cos of B, so that's the one that we had a look at. This is also going to be equal to sine. So a half sine A minus B plus sine A plus B. The second identity we could use is if we have sine A, sine B. Then that means we would just have a half of cos A minus B minus cos of A plus B. And as the third identity here, we would have sine No. Instead of sine, we would have cos. So cos of A and cos of B. This one, we would use 1/2. Multiply that by cos A minus B still, plus cos A plus B. Now, I'll leave this as an exercise for you guys to actually prove these identities. So the exercise here is to prove each identity here. So that'll be left as an exercise for you. All right. So that is going to be for the trigonometric integrals. So these ones are just going to be a list of exercises for you guys to try as well. So let's actually go through each of them. So let's have a look at the first one where we have the integral of 3e to the power of u plus secant squared of u du. Okay, so for the first one, shouldn't be much of a problem since we could break up the integral so that we have 3e to the power of u du plus the integral of secant squared of u du. And that would just be 3eu plus, so the integral of secant squared is just going to be tan of u and then plus c. So this one's not too bad. As for the second part, so let's have a look at part B. So we have the integral from 4 to 9 of root of x plus 1 over root of x squared, the whole thing squared, and dx out here. So let's go ahead and expand all this. So we have the integral 4 to 9. So the first one, we would just have x plus 2 times root x, and then 1 over root x, or that would just be 1. So 2 here. And then we have 1 over x. And then dx here. So we evaluate each of these. So the first one, we would just get half of x squared. The second one, we would just get 2x. The third one, we get ln of x, evaluated from 4 to 9. So this value would just be half of 9 squared plus 2 times 9 plus ln of 9 minus half of 4 squared plus 2 times 4 plus ln of 4. And you could evaluate this so that you could find this value on your own or try it. Okay, so as for the third one, we have the integral of secant of x. So although this might not look clear, we don't actually have anything that we could actually substitute with yet. Now, the reason I say yet is because let's say that we multiply and divide a term so that we could go ahead and substitute. So in particular, for this integral, I'm going to multiply and divide by a secant of x plus tan of x. And I'm also going to divide it by the same term. Now, the reason I'm doing this one is because if I expand this, so I have secant squared of x plus secant of x tan of x divided by secant of x plus tan of x d of x. So now I could just go ahead and apply a substitution here. So I'm going to say, let u be secant of x plus tan of x. And so that means du is going to be secant x tan of x plus secant squared of x. Aha, so now we see that this du, the secant x tan of x plus secant squared of x is exactly what we have on the top. And I'm also gonna not forget about the dx on the outside. And then the u is just gonna be the tan secant of x plus tan of x. So if we apply the substitution, we're just gonna get the integral of 1 over u du, which is just gonna be the ln of u. And so that's gonna be ln of secant of x plus tan of x plus c. Okay, so that's for the third one. For the fourth one, we have the integral of cos of ln of x. So this one's a little bit tricky. So let's try and see how we could actually approach this problem. Okay, so the first thing that I'm actually going to do is I'm going to directly go ahead and apply a substitution. So it's clear which one I'm going to be substituting. I'm going to be substituting the ln of x here. So I'm going to say, let u equal to the ln of x. So that means du is going to be 1 over x times d of x. Or that also means that x du is going to equal to d of x. But we have something that's an x here, and we have a du and x. So we're actually going to have to solve for x in this part here. Well, if we raise both sides to the e, so we have e to the power u, which is then equal to x. So that means if we put x is equal to e to the power u in, we would just have e to the power u du, which is equal to the d of x here. So applying that substitution over here, we're just going to have the integral of cos of x, or cos of u now, and the dx becomes the e to the power u du. Now, doesn't this integral look a little bit familiar here? So I'll rewrite this. Yes, because we actually evaluated this integral before. This was actually the last example from the previous lesson. It's exactly this integral over here. So that's the one that we have found. This is the one that we've gotten from it. So let's go ahead and just put that in, save us some time. So we have that. Let me go back to page. So we found this integral before, so I'm just going to put that in. So we have ex sine, or sorry, e to the power of u. And then we have sine of u. And then we also had a plus e to the power of u cos of u. And then we divided by 2. And then once we undo the substitution, so we said that, well, e to the power u is just going to equal to x. So let's go ahead and put that. So we have x sine ln of u, or ln of x, plus x cos ln of x. And all this is divided by 2. So that's this integral here. Nothing too bad because it's an example that we've seen before, but we're just going to be applying something a little bit trickier. Or something that might throw someone off. Okay, so let's have a look at part E. So we have a tan cube of x now. So also missing a dx here, so let's not forget about that. So I'm going to break the tan cube of x. So we all have the case that tan cube is odd. So m here is going to be the odd one. So I'm going to write this as the integral of tan squared of x, tan x dx, right? So now I'm going to apply the substitution for tan squared of x being the secant squared of x minus 1, so that we would just have the integral secant squared of x minus 1 of tan x dx, right? And so if we make the substitution that, well, if we let u be the secant of x, then that means secant or du is equal to secant x tan of x dx. Alternatively, so we want the tan of x here. So I'm going to divide both sides here by secant of x so that we would have du divided by secant of x. But that's also the same as saying du divided by u. So that's also equal to tan of x dx. So if I apply that substitution in, I'm going to obtain the integral of u squared minus 1 divided by, or multiplied by 1 divided by u du. So that means I'm just going to have the integral of u minus 1 over u du. So if I integrate and undo the substitution, I should just get a half secant squared of u minus ln of secant of x plus c. So this one should actually be an x. I'm also missing something over here. I'm missing the plus c here as well. Don't forget the constant. Okay, so that's for part E. Part F is also done similarly. So now we have a secant squared, secant cube of x. To integrate this one, I'm gonna break it up into a secant squared of x and a secant of x. So I'm gonna have the integral secant squared of x and the secant of x dx. So I'm gonna do the substitution that, well, secant squared of x is also the same as 1 plus tan squared of x and a secant of x dx. Then I'm gonna do the substitution for tan. So I'm gonna say let u be tan of x. So that means du is secant squared of x dx. But we have a problem. So we see here that, well, we have a problem. So we have a secant squared of x dx, but we want a secant of x here. So that's one problem that we are having a look at right now. So let's try something else, see what else we could do here. So actually, the substitution wouldn't actually be the right method, and this step wouldn't be the right one. So what we're actually going to do instead is apply integration by parts. Now, although this might look a little bit silly to use integration by parts, it would not be. So let's try using the DI method here. So we have the differentiation, you have the integration. And I'm gonna add the signs plus, minus. Let's see how far we get. What I'm gonna differentiate here is the secant of x. And what I'm gonna integrate is the secant squared of x. All right. So the integral of, so if we differentiate secant, we are going to get secant of x, tan of x. If I integrate tan, secant squared of x, I'm going to get tan of x. Let's leave it like that. So I don't need these two. So I'm going to, first of all, multiply the secant of x and the tan of x. And I'm going to subtract this by the integral of secant of x, tan squared of x, dx. All right, so now the next step here is that we're going to change the tan squared of x to secant squared of x minus 1. So we still have the secant of x, tan of x, minus the integral of secant of x, and we have the secant squared of x minus 1 dx. So now we would just have the secant x tan of x minus the integral of secant cube of x dx minus the secant of x, the integral of secant of x dx, right? Okay, so this should be a plus here. Now observe that we also have this secant cube of x. We have this as a secant cube of x. So I'm going to take this, bring it to this side here. So that means we're going to have a 2. And then we're going to divide it by 2. This integral we already calculated in one of the parts here, which is part C. So we calculated that before. So let's go ahead and put that in. So the secant cube of x I'm bringing to the other side. So on the left-hand side, I would have 2 times the integral of secant cube of x dx. This is equal to secant of x, tan of x. And we also have the integral for secant of x, which was ln of secant of x plus tan of x. And then I divide both sides by 2. So that means that the integral secant cube of x dx is equal to the secant of x tan of x plus ln of secant of x plus tan of x, whole thing divided by 2, and then plus c. Ooh, okay, so that one was actually a pretty tricky integral. So that's one way you could actually evaluate this integral is by using integration by parts here to actually go ahead and evaluate this integral here. So okay, so let me move this over. So there we go. So that's the integral for this one. All right. So for the 7th, for part G, we have something that looks a little bit odd here. Well, not too bad though, still, because we have that a trigonometric integral where this could be any number, and we have that m here is going to be the odd part. So once again, I'm going to break the secant or the sine cube of x into sine squared of x and sine of x. So we have integral sine squared of x, sine of x, cos half of x. I'll write it like this. All right. So now what we're going to do here is use Pythagorean's identity. So we're going to have 1 minus cos squared of x. And we have a cos half of x. And we have a sine of x dx. Now we're going to make the substitution that, well, if we let u equal to cos of x now, then that means du is equal to negative sine of x dx. So if we put that in, we get negative integral 1 minus u squared times u to the power 1/2 of du. So that what that becomes is, so we have the integral of u to the power 5/2. So I'm also including the negative sign, so just be aware of that. And then I have u to the power 1/2 as a subtraction here, and then du. And then evaluating these two, we would just have, well, 2/7 u to the power 7/2 minus 2/3 u to the power 3/2 plus c. Undo the substitution, 2/7. We let cos 7/2 of x minus 2/3 cos 3/2 of x plus c. And that's all for this problem. Not too bad. Okay, so let's have a look at the part H. So we have the integral from pi/6 to pi/2 of cotangent squared of x. Well, remember that the derivative of cotangent squared of x is also the reciprocal, or so we have the cotangent squared of x here. We could also rewrite this using one identity we should be familiar with. So remember that cotangent squared of x is cosecant squared of x minus 1, right? So let's go ahead and apply that. So we still have the integral from pi/6 to pi/2 of cosecant squared of x minus 1 dx. That's also the integral from of pi/6 to pi/2 of cosecant squared of x minus the integral from pi/6 to pi/2 of dx. And so what that is, so the first integral here, we know that the derivative of cotangent is going to be cosecant squared of x. So that means the antiderivative for cosecant squared of x is going to be negative cotangent squared of x. So that means we have negative cotangent of x evaluated from pi/6 to pi/2. And we also have, well, just a constant x from pi/6 to pi/2. So evaluating each of this, we would, well, cotangent, negative cotangent of pi/2 minus negative cotangent of pi/6. And we subtract that from pi/2 minus pi/6. So that we would actually obtain. So the first one's going to be 0, give you 0. The second one is going to give you positive root 3. And then for the constant term here, we're going to get negative pi/3. So that means the answer here is just going to be root 3 minus pi/3. Okay, so that's part H. Now let's have a look at the last one. We have the integral of cos 7 theta multiplied by cos 5 theta d theta. So this is actually where we're going to be using one of the angle identities here. So in particular, we're going to be using identity number 3, this one over here. So we're going to transform a little bit. So for this one, we're going to change this into the integral of half of, so we have cos of 7 theta minus 5 theta. We're adding cosine of 7 theta plus 5 theta. And this is going to be of d theta. So now we would just have, so half integral, for the first one, we'll just have cos of 2 theta minus, or plus cos of 12 theta d theta. And then evaluating each of these, so we get half. The first one, we're going to get half of sine 2 theta. The second one, we're going to get 1 over 12 of sine of 12 theta. And then plus C out here. And then we distribute the 1/2, so we get a quarter sine 2 theta plus 1 over 24 of sine 12 theta. And then plus C. Okay, so that is where I'm actually going to end today's lesson. So today's lesson was mainly just to work and practice evaluating integrals of trigonometric integrals and apply them using our techniques of integration that we have learned so far. So in the next lesson, I will keep on talking about the techniques of integration, but the next time we're going to be having a look at the trigonometric substitution. So if you guys have any questions, just feel free to let me know in the comments down below.